And today we have Mythic, which is our newest Open Access Coalition member.
Great. So thanks, everyone. We just wanted to introduce ourselves and talk a little bit about our plans for open access. So I have a brief overview of the company that would kind of give insight into the kinds of work we do at Mythic. Mythic is an AI compute company. So we're specifically focused on edge AI. We do this by doing full stack co-design. So we actually go from device physics, where we work with embedded non-volatile memories, and we work our way all the way through the compute stack up to new algorithms and applications. The company was founded in 2012 by Mike Henry and myself. Mike's our CEO, and at the time we were working with the Michigan Integrated Circuits Lab at the University of Michigan. Since then, we've raised $55 million from top-tier investors, including DFJ, SoftBank, Lux, and we now have offices in Redwood City and in Austin, Texas, not too far from the SI2 headquarters. And I forgot to update our employee count on this slide, but we're actually over 85 employees now. The compute that we do is for artificial intelligence, and AI is largely multiply, accumulate. So we're taking, or we're trying to process data by analyzing it against patterns, and these patterns are stored in what are called neuron weights. The neuron weights are stored in a large matrix, and you take your input data, multiply it by those patterns, and you get these outputs, which are basically how much did the input data look like the individual patterns. So this is, in a sense, similar to CDMA processing, if you're familiar with that. So the key operation is a multiply accumulate, or MAC, where we're multiplying two numbers together and adding it with other numbers. And so that creates this figure of merit. How many picojoules does that take to execute a MAC in the system? And so many of these systems compete in metrics like tops per watt or picojoules per Mac, which are inverses of the key for neural networks is the weight. So neural network weights usually number in the tens of millions. For an example here, we have a matrix operation with 1,000 inputs and 1,000 outputs that necessitates a 1 million weight matrix. And so these can be quite cumbersome to work with, and if you look at the energy draw and performance limitations in many of today's systems, they actually stem from managing these weights. So how can we get them to the compute? So we take a unique approach to that problem. So we use for the weights what we call a matrix multiplying memory. So we use embedded flash, and we operate on it using mixed signal computing. So this makes it so we never actually read that weight matrix. We take our input vector, and we're going to apply that input vector to our weight matrix using analog computing, and we'll get out an analog result, which gets redigitized. So this makes accessing the weight memory, which is the performance and energy efficiency limiter for other systems, to make that go away. This also has some advantages where we can eliminate the need of a batch greater than one. How many vectors are we processing in parallel? And then some other neural network constraints like CNN focus or sparsity. So just revisiting this matrix equation, so what we're going to do is replace these neural network weights with flash transistors. So this part here is going to be in flash memory in our system, and future systems might use RAM or PCM or other types of embedded non-volatile. And the other data, the input data and the output data, are actually digital. So our system is truly mixed signal, where the intermediate data, so the input and the output data, are digital, and the neuron weight data is analog and embedded flash. So we use these flash transistors as effectively like tunable resistors or variable resistors. So we work with and then this picture is this resistor array. And so when we access this array, we take our input data and we convert it from 8-bit digital values to 256 level voltages. That's on the left there with X0 to V0 and so on. And then the weights are stored as 8-bit values, the 256 level tunable resistors. And we can do that because we don't need to store weights for days. We can store them for a day or less and refresh them when we need to. Because this memory isn't truly for storage, it's really for compute. By putting these voltages across the resistors in this way, we generate currents on the bit lines, and we redigitize that using ADCs, stacked to digital values. So we have 8-bit digital in and 8-bit digital out. And this, the way we've configured the network and the way we've programmed these weights actually gives us that matrix multiply vector operation that we need as the bulk of our neural network computation. The top level architecture then is to manage that digital data that we talked about before. So we have a custom block, which we show at the top of this tile on the left, where it says weight storage and analog matrix multiplier. So that's effectively a flash memory structure, an embedded flash memory structure in a NOR topology. We've replaced memory peripherals with DACs and ADCs in order to give us that vector operation. That becomes a custom block with a left and a lib. And then the top level architecture is entirely digital, where we have SRAM, SIMD unit, network on chip router, and a RISC-V core. That on the left all forms a tile. So the design is tiled, and our top level actually just composes these tiles by abutment. So we place one tile next to the next tile and so on. So the top level APR flow is very quick. You could consider each unique tile its own APR job. But we only have a couple of unique tiles, so that makes things quite a bit easier for developing a large chip like this. The APR giant APR-ing this tile. That ends up becoming this reconfigurable compute array. So on the right side, we've got these green squares, and each green square is that tile on the left. And at runtime, this gets configured by a firmware and to perform one or more neural network operations. And so this is much like an FPGA, where you have a grid of compute that gets compiled to, much like an APR flow, to perform a fixed function. The system itself is a PCI Express accelerator. So on the edge, we have a PCI Express tile that controls a PCI Express PHY and controller instead of one of those memory compute arrays. On our chip, we run an inference model, and there's this data input-output relationship. So host system will send our chip a piece of data to be processed, like an input image, and then our chip will send back the inference results, like a series of bounding boxes with labels. So what this does for us is, or for our customers rather, is it gives us effectively a GPU level of performance for a edge form factor thermal and power limit. And so we have some benchmarks for existing systems, high performance GPU and a high performance SoC. And then we have some estimations of our performance and power in red. And so our system should perform like an off-the-shelf high-performance GPU. In this case, ResNet 50 is a classic image labeling algorithm. And so we can run this at 900 frames per second, much like a $1,000 GPU. But instead of drawing 167 watts, we can draw 2 watts. And that opens up all sorts of possibilities about where this AI capability can be deployed, because you can't put a $1,000 167 watt GPU into every camera system, but you could put a 2 watt chip in every camera system. And so it really impacts the number of places that AI can be deployed. Oh, so GPU performance. Anywho, so at Mythic, we're looking at using open access very heavily because, as I showed earlier, we have this a very large amount of custom design and a very large amount of RTL-based design, and the system's almost 50-50. And so we'd like to use open access to enable and enhance our cross-domain integration between these two. We have great design teams, but this boundary between custom and RTL ends up being one of the danger points. So when you make a mistake in your system, where is that mistake going to be? And often it's at the seams between things. And this is one of our biggest seams. We'd also like to use this as part of a regression testing flow. We have a very strong emphasis on regression testing. Open access will allow us to make much deeper regression testing hooks, especially for our custom design flow. And we're also looking at using an OA partitions feature in the latest OA release. I think this is my last slide, so I'd be happy to field any questions.
Yeah, so Tom here, I guess I can just maybe provide some extra detail if anybody needs in terms of questions. You know, we're running our regression on a continuous integration model. So speed and performance of the computing with the design data is what I feel open access brings very much to the table, and I'm really excited to be using it.
Yeah, you mentioned on slide 10 there was a high-performance SoC. Can you expand on what that was? And this is Roger Carpenter and Paul Rodman at Google.
So I can't talk about what that SoC is, other than it's one that you'd normally see in say, like cell phones or like camera systems, like your smart cameras. But I can't tell you which one it is because the licensing doesn't allow benchmarking.
Sure. Okay.
And what if you wanted to do, this is Paul Rodman, so what if you wanted to do higher resolutions and lower frame rates?
Our system supports a variety of resolutions. I think that really depends on how the application uses memory, because there's a limit to the amount of memory in the system. So I believe we can support 4K, but our target is for high performance 1080p. 1080p is kind of the gold standard in the security space, because when you go to higher resolutions, the camera sensors don't get as good because the pixels get smaller on the silicon. So larger pixels work better for low lighting conditions. So we're really focused on 1080p, but we can also support higher resolutions as well.
So do you have any benchmark results for 1080p?
Not off the top of my head. It's basically almost proportional to the number of pixels. So
okay, that's reasonable.
So it'd be 24 times slower, so 900 over 24. So we'd expect about 34 frames per second, or 38 frames per second.
Got it. Thanks.
Other questions?
So the previous couple slides earlier, you had an array. That green tile has within it a flash array and a bunch of A to Ds and D to A. Is the density of the flash array limited by the aspect ratio of the A to Ds and D to As? Or how do you maintain a high density? How high is the array in each tile?
We did 1,024 inputs and 1,024 outputs.
Okay.
And then there's you have to do column multiplexing like you would on SRAM, because you're trying to fit a ADC in like a fairly narrow pitch.
Okay, so you keep the density of the splash array at very high. You don't have to reduce the density.
That's correct.
Yeah.
We what we do is we get an off-the-shelf array, and then we replace the peripherals. But we use multiplexing in order to get around the density issues that you're talking about. But I think they also do that in the memory arrays originally anyway, just because you can't fit like a sense amp in such a narrow pitch.
Right.
Mm-hmm.
Okay.